Hello, everyone, and welcome to another episode of Quantum Walk Wednesdays. I'm Uri, co-marketing director from QSI Toronto, along with my co-marketing director, Isabella. Today, we are excited to have with us Amir Naveh, co-founder, CPO, and head of quantum algorithm at Classiq Technology. Welcome, Amir.
Hi, thank you for having me.
Could you tell us a little bit about yourself?
Yes, for sure. So, Amir, I'm from Israel. My background is I studied physics and computer science, then spent a bit more than a decade in the Israeli Defense Forces doing software and algorithm projects for Israeli space program and also for some intelligence initiatives. So this was a chance for me to do quite large software and algorithm development projects, both the development sides and also the management parts of actually making the project provide real impact. And then in the past 4 years, together with my two co-founders, Nir and Yehuda, we formed Classiq, which is a quantum computing software company. And I'm currently the chief product officer of this company.
Wow, thank you, Amir. So first off, can you tell us about the founding story of the Classiq and the vision behind the company?
Yeah, for sure. It's always interesting to go back to the origins.
Yeah.
So I was part of the CPO program, which is a program that quite a lot of people that finish it because of a lot of the tech background, they try to build or found a technology company after they finish with their Defense Forces service. So myself and Nir, who is now our CEO, we thought of building a large technology company. And we spent a bit more than a year looking at different domains, and we were always a bit frustrated that things didn't look like a huge opportunity. Always some specific problems in some specific markets, but it seemed like the impact would be limited. Our third co-founder, he is also my father, Yehuda. He was leading the IBM efforts in quantum in Israel. And after discussing quite a lot with him, we understood that quantum software is a huge challenge. A lot of companies are developing the hardware, but building software that actually scales is something that no one is doing properly. And here we thought this is a really big opportunity. This is something that could actually make a large impact. Of course, it has risks because quantum computing is not yet commercially impactful. So the market is limited, but if it happens, the potential is almost unlimited. And this got us very excited. And after a few months of kind of understanding what is the real problems and pains here, then we were able to form the company and get funding for it.
Thank you. We were wondering also what some of the key innovations Classiq has introduced to the quantum computing field were.
So here is the basic vision maybe of Classiq, and here is where most of the innovation comes. When you are building a classical algorithm, you don't talk directly with the hardware. No one is wiring transistors, and even no one is wiring specific registers or doing any memory management. You write your classical algorithm, and between your thoughts and actual processes running on the machine, there are many layers of abstraction and automation that make all of this possible. And it's not limiting you as a developer, it's doing the opposite. It's giving you power to focus on what you want the computer to do and not on how it's doing it, which is typically a very hard problem. If you were forced to write your classical algorithm directly on transistors, you would be hugely inefficient. And this is a problem in quantum as well. Even though it's a different logic, it's the same fundamental problem where in the end you need to interact with qubits. You do this through quantum gates. But if you are forced to write an actual application using the individual gates, you will not get very far. You will find yourself making a lot of decisions that you actually would want abstracted away from you and letting a strong technology decide for you. In the classical world, we call this sometimes operating systems, sometimes compilers. This is what these levels do. So the innovations that we bring are exactly in this field. So if you have a quantum function, whether it's quantum arithmetic or controlled logic or exponentiation or any of the other common constructs in quantum, then when you use Classiq's technology, you are getting a much more efficient solution while not having to describe the exact implementation. You let our technology decide it for you without losing any expressive power. So this is the key innovation, and most of what we are doing is centered around this.
Thank you. And could you tell us how these innovations improve the efficiency and effectiveness of quantum algorithm development?
Yes, for sure. So Classiq is working already today with quite a lot of customers, dozens of enterprise customers, and a lot of research and academic users. And what they typically do with the platform, first, it's ready and available, and you can use it. So if you're an enterprise customer, you will need to pay. If you're a researcher, currently it's completely open and free, and you just enter the platform and you start using it. So this is one advantage where sometimes some of the products are in kind of beta mode and it's hard to use them efficiently, or sometimes the interfaces change very frequently, so it's hard to get a real project going while underneath everything is moving all the time. So this is a stable product, and what it enables the users to do is to actually implement the quantum algorithm. So I don't know if any of the listeners had, by any chance, ever tried to implement Shor's algorithm to actually implement it. So the concept is clear. What you're trying to do in essence is do modular exponentiation with quantum Fourier transform after it, more or less. So this is the basic building block of Shor's algorithm. But now you need to implement modular exponentiation in actual software. And you want to do this not for 3 or 5 qubits. You want to do this in a way that actually, uses the real logic behind Shor, and in a solution that won't scale exponentially with the number of qubits. That's missing the point. And turns out to do this modular exponentiation, you need to do modular multiplication. And for this, you need to do modular addition. And in each of these steps, you have many decisions. And so implementing this is very, very hard. So I really recommend you can view our documentation or our GitHub repository, and you can see how Shor's algorithm is implemented with Classiq, and you will see how it leaves the essence of, okay, this is what the algorithm is trying to do, but at no point are you required to allocate the different auxiliary qubits and make all the infinite number of decisions required to actually implement this very complicated logic. And it actually works. So like this example, I can give many more examples in specific industries, in specific applications, but this is the basic usage of having the algorithm in mind and being able to create it while not describing it at the very explicit gate level.
So what are some practical applications of Classiq technology that you're most personally excited about?
So I love the work with the enterprise customers because first, they have very strong teams, most of them. These are teams of experts that are devoting their full time and energy to quantum applications. And what's more important is that they are connected with the business people at the organizations. So usually the problems have a flavor of something that is actually commercially interesting. So some examples that I'm able to share, for example, so work with Rolls-Royce on computational fluid dynamics. So if you are trying to create new engines, you need to kind of simulate the dynamics of how these interact with air or other, moving parts. And this is a really hard problem, typically done with like a numerical analysis that doesn't scale very well. And if you use the HHL algorithm, it has potential to scale better than classical algorithms. So we're working with them on how you can actually scale this problem and simulating it on a very large number of qubits. Also, other example that maybe I can share is kind of on financial use cases. So we're working with them in Intesa Sanpaolo from Italy, and also with Torino University. You have many different assets that you can price, and the more that you try to actually take into account the actual dynamics of how the market is acting, the problem becomes more and more complicated. So kind of a lot of people are saying this headline of, derivative pricing or option pricing, for example, but when you're actually looking into trying to model the actual market dynamics, when the problem becomes real, then the quantum algorithm becomes much more complicated and nuanced. So it's a good example of how doing the simple case of just giving, some example, that's easy. But making the actual commercial application with the actual real world logic embedded inside, this becomes very, very hard. So this is exciting for me as well to see how kind of it's a real world problem and not just some thoughts that stay at the very conceptual level.
Oh, wow. Yeah. Thanks so much. I was thinking about I'm most excited about for me is the finance industry and the quantum computing as well. And what are some of the biggest challenges you face in the deployment of the quantum computing solution, and how do you approach that?
So I think the number one problem or the number one challenge is that, the hardware is not very strong currently. It's very limited. Depending which hardware you're using, ion traps have better fidelities but are limited to, the Quantinuum machine just released is the largest with 56 qubits, and IBM has a bit more qubits, but in the end you're limited to a few hundred 2-qubit gates. So you can't really test large circuits or run them or expect any meaningful results on current computers. This creates a big challenge because you need to kind of develop something that is viable for when these machines do exist, but you're testing it on either very small devices or on simulators. So this is the challenge. I can't say that we fully have a solution for it, but I think the ways that we deal with it is first we acknowledge this is a challenge, but if you are waiting for the hardware to be fully there before you start developing the applications, you will fall behind because it takes a long time to gain this knowledge and expertise and technology. And still, I think working with simulators is quite interesting, and also just achieving the theoretical results. So we can create circuits with thousands of qubits. We can check how many resources they need. We can verify that they are correct. And then how well they will actually perform this, we will need to wait and see, but at least we have some benchmarks of how we are advancing. But this is a big challenge. It's not a full solution.
Thank you. We were also wondering what advancements do you anticipate in the quantum computing field over the next 5 to 10 years? I
usually don't like to give too long-term predictions on things that first are out of my control, but second are very largely debated. I think when you look at the hardware roadmaps, IBM, Google, IonQ, Quantinuum, QEra, Pascal, a few others, all of them are quite optimistic for the next 5 to 10 years. So in all of these roadmaps, you see either a commercial advantage possible with maybe thousands of qubits with high fidelity. Some even talk about error correction. So this is exciting. I think it will be interesting to see how it advances. Classiq has the advantage that we need one winner. So if it's Quantinuum, that's great. If it's IBM, that's great. If it's QEra, that's great. If it's any other gate-based company, that's fantastic. So I hope, like all of the industry, I hope there is success there. And I also hope there is continued success and research in the quantum applications and algorithms domain. I mean, I think what Google has done with the X Prize and other initiatives here that are trying to go from the applications downwards, I think that's also an important advancement that will happen hopefully in the coming years.
Yeah, thank you so much. 5 to 10 years it's hard to predict, but it's great to hear from your perspective. Last question, what advice would you give to students and professionals for interested in pursuing a career in quantum computing?
So I have kind of two contradicting advices. One is the ecosystem today is dominated by people from academia, experts in quantum, either from the physics domain or from the computer science domain. So I think the best and most natural way to pursue a career in this industry is to get expertise in quantum computing, either through physics or through computer science, and kind of interact with the leading researchers there, try to find a group that is already established in this field. There are quite a few, and then find your path from there. So this would be my first bit of advice. And the second, which is a bit contradictory to this, is that I didn't have 4 years ago any specific expertise in quantum computing. I studied physics. I had a background in algorithms, and I found this field to be hugely exciting, and I jumped in. And I learned kind of as we ran forward. And I think if you have interviews with Jeff Bezos, not that I'm comparing myself to Jeff Bezos, but he was saying when he founded Amazon in the year 2000, I saw this internet thing, maybe before, 1995 maybe it was, I think it became public maybe in 2000. He said, there is internet, it's growing 10,000% year over year, I need to be there. So he left his comfortable job and he just went and founded an internet-based company. And I think there are many different niches in quantum that you don't need to be an expert in everything to just enter into them. So specifically in quantum software, you can understand quantum algorithms without being an expert in every detail of the physics underneath. If you're really passionate about this, then be like Jeff Bezos and leave your other hobbies and other professions and just start doing something, whether it's within a company or within any other place, and you will learn what you need as you go, but just go in there. Maybe 10 years from now, it will be a missed opportunity if you don't do it. So that's kind of also my view on life. Don't wait too long to start. Just start and you will also learn faster that way.
We were just wanting to know if you had anything else that you wanted to share with our audience today, or just basically opening the floor to you.
Yeah, so I have one personal passion within Classiq. I mean, I have a few, but let me share one, which is we have something that we currently call the Classiq Library. It's a public GitHub repository. It's open source, it's completely open. You will find there every quantum algorithm and application that you can imagine. Shor's algorithm and Grover's and HHL and applications for finance and for chemistry and for logistics and for optimization and for any of the things that you may have read about or studied. And all are actually implemented with Classiq. And I invite listeners to do two things. One is to explore it and open the GitHub, give us a star, of course, but go and explore and view the different algorithms and applications. It's a great resource to learn, I think. It's it's probably the most comprehensive actual, coded implementations of quantum applications and algorithms, and they're very well explained. And second, because this is open source and it's built as a library, you can contribute. You can build your own quantum algorithms and applications, and our team will be very involved in guiding you towards working with our technology in order to build your new algorithm. So I welcome you to do both these things, and personally, I'm very happy to hear any feedback on anyone that chooses to do this.
Well, thank you very much for joining us today on our episode for QWW and for introducing us to Classiq. Thank you for coming.
Thank you for having me, and thank you for the wonderful questions. It's a great opportunity to share a bit more.
Thank you so much.
Thank you.
Thank you very much for watching this episode. And don't forget to subscribe to our YouTube channel if you would like to keep up with our work, as well as subscribing to our Instagram, qsci.toronto, so that you may know who our next guest speaker is. So see you next week.
Yep. Bye.